Oh, I need to put those up, don't I? Alrighty. So today is Kevin's review. Kevin is the only one to kind of give questions. I guess he gave a couple yesterday. So, let's start with the actual questions that you asked Kevin, and then we'll go for the others. So we have tin 2 plus 2 iron goes to tin 4 plus 2 iron 2s. And we're given that the E is 0.617 volts with the extra volts on the other side. Okay, we're looking for what is E when when these guys equal 0.5, and then when the other ones are 0.1. Alright, and I think this is the one that I had put the wrong answer choices for, because stupid ACS makes me do this. Anyways, the what we're going to want to use for this one, or 0.592 for 2 n log q. Either one will work. What's important here is that we understand that we have we're going to need q, right? So q is going to be the tin 4 plus and then the iron 2 plus over the tin 2. So that'll be 0.10 cubed, 0.5 cubed. So whatever that happens to be. So if we want to do this, oops. That's what I needed. So whichever way we do this, we have 0.617 minus 0.0592. We have 2 electrons in this process. How do we know that? If you really want to do half reactions, you could. But you'll see that we have tin 2 plus going to tin 4 plus. So that is going to be very clearly 2 electrons, right? Or you have 2 iron 3s going to 2 iron 2s. That's another 2 electrons. And then so we have log of Q, and apparently we've got Q as a numeric answer. Doing this, I got apparently 0.68 volts, which was not an answer choice because I had put the wrong answers on there, but that is the right one. And I think, so I've updated the question, so I think if you take it again, it might fix it. Though it was saying that if it's already being used by a quiz, it's not going to update, so maybe it won't update, but suffice it to say, if you try it and you get it wrong, it's because of this. So I think I got 0.68 volts, and so yeah, so then you did it right. Hooray! So I guess I have to double check that all the answers are right for the real final. Bleh. Alrighty. Let's look at your other question. We're ranking these from most soluble to least soluble. Remember, we can only compare solubility in terms of molar solubility. So we have barium nitrate with its KSP. So if we just kind of figure out what the molar solubility of that is, it's going to be the cube root of that number, right? 4.64 times 10 to the negative 3. 2 is also a cube root, so we're looking for a cube root of 7.2 times 10 to the negative 15. And then 3, we're looking at just a square root of 3.13 times 10 to the negative 11. Bust out all these. So 4.64 e negative 3 to the 1/3 power. 0.167-ish. 7.2 e negative 15, also to the 1/3 power. 1.93 times 10 to the negative 5. And then 3.13, oops, 3.13 to the negative 11. To square root it, we get 5.59 times 10 to the negative 6. And so this will be most, second, and least soluble. Oh, I'm glad you already did the stuff, and here I am buzzing out of my calculator. And so they're in order already, so that is our answer. So that was the only tricky bit there, was the cube root versus the square root for KSP. Remember, KSP is going to be the product of your ions. It's the ion product. Solubility product is what it's called, SP. So for example, it's something like this. That's why we have a cube root. So because we have a cubic function there. All right, so that's that. So now we have the generic review of kinetics and buffers. Let's do a... Okay, let me pull up the questions for the practice exam. And I guess we can just do a couple that might fit in that one from the like ACS practice, I guess. Because again, those are going to be kind of the most common, or like most applicable, I guess. There we go. Alrighty, so let's see. What's a good one? Alrighty, here's one from kinetics we can go over. If this is useful to you, Kevin, I mean, I haven't checked if, you know, these are things that you've gotten right or wrong as you did the practice. So let's see. I just had one. Where did it go? All right, here we go. If this is not useful, then we don't need to worry about it. All right, so it says activation energy is 111 kilojoules per mole. Yeah, so I don't know how useful it would be to review it in an hour. Probably the best thing to do would be to look at the old videos somewhere, but we can kind of just go over them. So yeah, the rate constant at 300 Celsius is 0.54. At 300 Celsius. And then we have what's K2 at 310 Celsius. So that's, of course, 573, 583 Kelvin. Cool. I really am terrible at writing numbers. I just said 583 and I wrote 783. Doesn't make any sense. So we have just a couple things here to make sure of. So we're looking at K2, right? So scam likely is calling as always. So we have this is actually, so EA times 1 over T2, no, T1 minus 1 over T2 over R. Remember that EA is in kilojoules, R is in joules. So we can solve this. 0.54 e to the 111,000 times 1 over 573 minus 1 over 583 divided by 8.314. Or just take all this crap and multiply it by 0.54. And so K2 is going to be, I don't want to calculate it, but I have the answer. It's 0.81 molar per second. I'm sorry, per molar per second. So there we have it. So just math, but let's see if there's ways we can kind of finagle this. Obviously, we can eliminate the answer choice that has the same rates. We know rates go up with temperature, so we do not need to worry about that. There's another answer that has a very low rate, one that's lower than the initial rate or original rate. That should also not be an option. So really we have two choices. We have one that's slightly higher than the original rate and one that's a lot higher. This is a slight temperature increase, so if all else fails, guess at this slightly higher rate. I mean, why not? So if all else fails, you're out of time, use logic, get through the test that way. Let's see. Just find other kinetic stuff. Remember, a zero order reaction, actually it'll be linear in the opposite array. If you're looking at a zero order reaction, remember that you're looking at just a downward slope when you look at A over T. If you're looking at a first order reaction, you're looking for the natural log of your concentration. That one should be straight. And then for a second order, you're looking at the inverse, and that'll go up like that over time. So just remember your graphs are like that. If all else fails, you have the equations there. So you have natural log in your first order when you have 1 over in your second one. So hopefully you'll remember that. Yes, calculating the slope is a pain in the ass. But remember, for calculating the slope, that's just KT or negative KT depending. Or rather, K is going to be your slope, right? So you can figure it out based on just rise over run. Or if you have the formula for it, it's just whatever your K is, right? So we have that. Let's see. What else for kinetics do we have? Hopefully you guys remember the... Here, let's see. Do we have a problem that I can give on this? Remember that radioactive decay? By the way, they put the questions on radioactive decay in the kinetics chapter, but just remember that decay is always a first order reaction. So just recall that. Let's see. Let's do one of the ones where we have to do the reaction order. Here, let's pop open the book. And looking at the initial rates, let's go ahead and do a problem like that. Okay. Acid-base equilibrium, who cares? Equilibrium, who cares? Okay. Alrighty, here we go. Let's do, I don't know, 14.35 from the book. So with this problem, it's just one of those big ass data tables that we're looking at to find the order of the reaction with respect to each particular component. And so we're going to be looking at how things are changing as we change our reactants. So we have that table. We have 5 data points. We have initial rates. We have concentrations of the 2 reactants. And we're going to try and find the rate law. So remember that with this, we're looking at if these things are going to be to the first power, or if they're squared, or if they are cubed, right? So we're going to be looking at what's happening here, raised to whatever power. So, for example, if we look at the first 2, we have ammonia is changing by half, right? It's going from and we're going to have that value is going to be our initial rates, right? 20, 130, 1065. If we do this, we have 2. Lucky us. So X is 1 for ammonia. So easy one. Maybe we should try and find a harder one, but whatever. It's all the same. Alright, if we try and find, if we look at experiments 1 and 3 for this one, and looking at, let's actually find one where ammonia is not the same. Here, let's look at 3 and 4. We could look at 4 and 5. 4 and 5 would be a little easier, but let's pretend we didn't have 5 there. Let's look at 3 and 4 instead. Here we have 0.0682, 0.1193. So again, sorry, I don't want to copy all this problem up, but it's just this big old chart of numbers in one of the questions of our book. Oh gosh, this is going to be hairy, but let's see. 0.2. Oops. 2 divided by. Okay, so we have 0.571 to the y power is 0.0684 divided by 0.1193. We get 0.573. Guess what? Yes, it always gives everybody difficulties. There's essentially the same thing, so y is also 1. But if we looked at numbers 4 and 5, we'll see that we have a doubling for the doubling. So, I'm sorry, 3 and 5. So you'll get the same value there. And so that's for boron trifluoride. So for this particular reaction, they're both first order, and so that is our final value there. So you just solve these and what? Okay, I don't need you to have volume anyway. Let's see, what's another one we can do based on this sort of thing. What else would connect? Let's do one more. Do we want to do, let's see, boring. What else do we have that we can give? Oh, why don't we do that decay one? Yeah. All right, so, oh my gosh. So this is a problem on your practice exam. It has, oh gosh, I'm going to try and draw this. How many dots is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Okay, so we've got 12 dots in here. Okay, and that's at T0. At time 3 years, we have I'm going to just use colors because I can. T equals 6. We have and then we have 9. This is going to take me more. Actually, we don't have 9. We're looking for 12. So, this is kinetics, but it's also radiation. Why not? Same thing, half-life, right? If we look here at what's happening, we can see, hopefully, that this is going to be a half-life here as we go from 0 to 6. Right? We see that half of it has become the black dots and half of it is still the white dots, which implies that 6 years is going to be our half-life for this. And so if we're looking at 12, we need another half of those to go away. So if we had 6 black dots left, we're only going to have 3, and they'll have turned into blue dots instead. 4, 5, 6, 7, 8, 9. And so as a result, we're looking at whatever answer had 3 black, or 3, I'm sorry, there are 3 white dots left. The ones that I've drawn are black dots, but those are the white dots there. So we're looking at the one that has 3 white dots left. So more conceptual question there. Let's see, what else do we have here that we can go over? All right. We have that one with the trend or the reaction coordinate diagram. And then we have this thing. We have another one in there. All right, and we're told that this is 10 kilojoules. That's 35 kilojoules here. And then we have 15 kilojoules. Gosh, I'm terrible at drawing these. So it's asking about the catalyzed. You don't understand the half-life one. Okay. So half-life is the time it takes half of them to break down, right? So if we look at the ones that were given, so that's 3 and 6. This is kind of what we have to start with at T0. We have 12 that I've drawn as black and 0 blue ones. If we look at 3 years, we have 8 black ones and 4 blue ones, because I don't know how to write. And here we have 6 and 6. So we know, therefore, if we look at time 0 and time 6, that's where we've lost half of our stuff. We have lost half of our original 12 black dots. They have turned into blue dots. And so that's a half-life. We have reacted or decayed or whatever half of our sample. So we had 12 black dots. Now we have 6. That's 1 half-life. So that's 6 years. So if we're looking for 12 years, 12 years is 6 years after 6 years. Yeah. So if we were looking at T18 years, we would have 1.5 black dots left. Obviously not really possible because they're dots. You can't have half a dot, but that's what you're looking at. Yeah, so each half-life, which is 6 years according to this, is where we're going to do that sort of thing. Yeah. And if you were to look at 24 years, then it would be 0.75 dots left. So you just keep 1/2 divided by 2 every 6 years, according to this particular one. So that's why at T12, we're going to end up having half of 6, which is 3. And then we're looking at 9 blue dots. So that's the picture we're looking for in this one. All right. No, which I think is a big mistake. I think 3 students have taken it out of, what do we have, like 15 or so? So, not good. 20% of the class has taken it. Like I do suggest, though obviously you are the ones who are here, you are the ones who have probably taken it. I would suggest at least opening it just to see if you can see all the images. Because, I mean, you've taken it, Kevin. You saw how many images are there for the practice exam. And there's graphs everywhere. There's dot pictures like this. There's pictures of things that are, forming precipitates. There's all sorts of pictures. So you want to make sure that your computer or whatever you're taking it on is... Yeah, you want to make sure it's going to work. So that's why I kind of gave the extra 5 minutes on the timer there to make sure that everything's going to load properly. So, what do you mean like when you had to load them? Does it just say like image loading or something as you were going through it? So hopefully 5 minutes would be enough time for that to take place. I don't know if there's an actual like button you have to click. There's a JPEG thing you have to do. Okay. So hopefully 5 minutes would be enough to like allow that to happen. So I definitely suggest people who are watching this who have not taken the practice exam, probably not going to happen because why would they watch this then if they haven't taken it? But preaching to the choir here, but at least open it so you can get a feel for it and get a feel for the timing. So it can do nothing but help you. So yeah. Anyways. Let's see, what else were we gonna... Oh, we were doing this reaction coordinate thingy. So it says, we're talking about, I think, the catalyzed pathway here. What is these things? So, when we're looking at a reaction coordinate, let me simplify this. Remember that this is, of course, energy as an axis. Your initial line there is your starting energy. So that's the total energy of your reactants. And so as you go through this, there is some energy that you put in called the activation energy. And that's going to be what this hump stands for. That's your activation energy there. So the difference between your starting energy and your transition state energy is your activation energy. Remember, up here is where we have your transition state. That's the double dagger thingy, sometimes with a star. I'll just write TS actually. We'll just make that a little bit easier. So your transition state up there is your highest point. The difference between your transition state and your starting state is activation energy. And so the change in those two is your activation energy, right? When you're looking at the other thing, which is the energy of the products, remember that enthalpy is the energy of your products minus the energy of your reactants, right? So this is going to be delta H there. In this case, it's because this is a graph we're looking at in terms of magnitude, but we're going to see our products have lower energy, which is why it's going to be a negative 15 kilojoules there. So they have lost 15 kilojoules from our initial to the end. Remember, this is a state function. Doesn't matter what our hump is, it's going to be constant. So when we have the catalyzed pathway in here, that lowers our activation energy. And it also increases your rate constant because of lowering that activation energy. Delta H doesn't change. Wow. Remember, delta H is a state function. State function means it does not matter what pathway you take, it's always the same. It's path independent. So your catalyst will lower your activation energy and it will increase your rate constant. But it's not going to change delta H. And it's of course not going to change delta G or delta S or any of the other ones, which are also state functions. But in this particular one, we're looking at EA and delta H. So we're looking at what describes the catalyzed one. And it's told us that this amount here, terrible at drawing, but that's 10 kilojoules. So our activation energy is going to be 10 kilojoules, right? That's the difference between the top of your hump and your starting energy, which is given to us with that little section there. Delta H is the same as it was before, which is negative 15 kilojoules, because it's exothermic. We can tell from the graph that it's exothermic because products are lower energy. So we have lost energy through this reaction. And so the answer choice we're looking for is the one that has these two values. So 10 kilojoules as well as negative 15 kilojoules. And so that's what we're looking for there. So that's another kinetics one, I suppose, reading those diagrams. There's a lot of those diagrams if you haven't been able to tell. Remember, an endothermic one would look the opposite. This is an endothermic one. You'd still have this value being delta H. And this value would be your activation energy. If you were to have a catalyst with this sort of thing, it would look much the same, except we're going to have just a smaller activation energy. And so, but it's still going to be endothermic. It's still going to have all the other same properties because, again, delta H is a state function. It does not care if you have a catalyst or not. Remember, this is the transition state up top. Not an intermediate. That is a transition state. This is a one-step process. If you have multi-step processes, something like that. Let's just say this is exothermic. It's very slightly lower than the initial one, it looks like. So delta H is negative. We have activation energy 1 here. And then we have activation energy 2 here. So remember here, we in this particular graph, we have a transition state up there, a second transition state up there, and in the middle we have our intermediate. And our intermediate there can be isolated. Remember, intermediates we can capture, transition states we cannot. Intermediates there, a second activation energy is as if we were just taking this and now we're starting with our intermediate. And so we're looking at the intermediate's energy versus the second hump, and that's going to be our second activation energy. We'll technically have 2 delta H's here if we wanted. Remember that according to Hess's law, we can add delta H's up. If we wanted to look here, that would be our first delta H between the initial case and the let me make this a little bit more clear. And that, oh god, that's terrible on the top too. So that's going to be our delta H, our first delta H from the starting material to the intermediate. Our second delta H is going to be from the intermediate to the product. And overall delta H would be the sum of those, right? So we can see delta H2 is a little bit bigger. That's the one that's exothermic. That's the one that's negative. We see delta H1 is positive, but delta H2 is a larger magnitude. And so that's why overall we have a negative delta H at the end of the day. What else can we say about these sort of graphs? I don't know, that seems to be all of the important bits there. Let's see, what else do we have? Mechanisms, I guess we can talk about. Remember, if you have your slow step first, let's just say this is our reaction. Your slow step is rate determining. And so therefore, the rate will just depend on your, and yes, in this case, C would be an intermediate. Yeah, for sure. And so you would just have your slow step determining your rate, and that would be the easy way. But of course, we never asked that, right? However, often we like to throw these at you. I'm too fast for you. So if we, yeah, I beat you to it. If we have the opposite one, we have our rate determining step as the second step, which would tell us that the rate is C times D, but C cannot be included in the rate law because it's the intermediate. So what we do is we substitute. Remember that for our second one, we have that the rate for the first reaction could be written either way like this. And so if we were to solve for C, solving for C gives us and we would need to plug this back in. So we would end up with our overall one being rate times K times K1 over K negative 1 times A times B times D. Whatever this happens to be. And of course, we just get rid of all this crap and replace it with a new K. And so, yes, indeed, we would end up with KABD for our, exactly, combining the Ks. So, perfect. So, if we have something like this, our rate law should end up reflecting the fact that it is based on the intermediate, but we're going to replace the intermediate with our actual initial products, initial reactants, sorry. And so that's what we would end up with as our rate law for this particular scheme. And of course, if we had any coefficients, let's just say whatever, let's say now we have 2D, it would still have D squared in our product, whatever it happens to be. So remember, this is how we can end up with half or something, or negative numbers in our rate laws as well. So we have those options there. All right, let's leave kinetics for now. Take a look at the old videos. Bring questions written, I guess, and I can answer them in a written way. Let's talk about buffers real quick. First things first, they have to be made of a weak acid and its conjugate base. So no other option there. It has to be one weak acid and its conjugate base. Acetic acid and acetate. Formic acid and formate. Benzoic acid and benzoate. Whatever. Oxalic acid, oxalate. You need some sort of weak acid and its conjugate base to make a buffer. Remember, for a buffer system, we have the equation of Henderson-Hasselbalch, where we would use the pKa and then the concentrations of each one to get the pH of the solution. Remember that pKa is just negative log, Ka. So, in case you have that, and so you just want to look at these sorts of things. Remember that buffers will prevent pH change. That's what they do. By reacting, your weak acid can react with any added base. Your conjugate base can react with any added acid. Let's find a problem from the practice exam we can look at. This is all equilibrium. Equilibrium. Where's some acid-base stuffs? There we go. Buffers. Buffer. Oh, let's not forget isotables too while we're at it. Aha, okay, here's one. So what combination can be used to make a buffer with a pH of 4.2? We have Ka of benzoic acid and Ka of hydrocyanic acid given to us there. Let's go ahead and find their pKa's. For benzoic acid, we're looking at negative log of 6.5 times 10 to the, negative 5. So we get pKa is 4.187. I'm terrible at this. And for HCN, honestly, we can get rid of it because its pK is going to be way higher, but let's go ahead and do it anyway. Negative log 4.9 times 10 to the negative 10. If we want a pH of 4.2 for our buffer, we would want something that has a pKa around that area. You want your pKa to be within the buffer range, which is plus or minus 1 unit of this. So we want our weak acid pKa to be 4.2 plus or minus 1. So somewhere within there. So obviously we're going to choose benzoic acid as our choice, right? Hopefully we can see that the HCN... Oops. Oh my gosh. We're going to choose our benzoic acid, right? So that's going to have the better choice there. So our option choices, first off, we can eliminate 2 of them by having HCN there. There's no need to worry about that because who cares about HCN? So if we wanted to make a buffer out of this, we have 2 options left. We have we have 50 mils of our HA at 0.5 molar. And then we can either add 25 mils of NaOH at 0.5 molar or 50 mLs at 0.5 molar. If we do the first case, The first case will end up giving us, we'll have 25 essentially mils left. I guess these would be, no, they would be the same, yeah. Essentially, if we're just looking at this, you can calculate the moles if you really want to, but essentially we'll have used up half of our HA and now we've turned it into A minus. So that would be a buffer, which would have a pH or a pKa or a pH around 4.187 because it's equal amounts. That's what the pKa is. Remember, half equivalence. If you look at option 2, we essentially would have just A minus. That's not a buffer. We have only A minus, so that's just a salt solution. So that's not even a buffer. So if we've completely neutralized our acid, it's not a buffer. We need to have the other one. So first things first, eliminate the acid that has a way different pKa than the pH you're looking for. And step 2 is just understand that one of those options will get rid of your acid completely, and the other one will leave you with both acid and conjugate base. So because it's a buffer, it has to have both of them. So you're looking for the one where you add 50 mils plus of benzoic acid and 25 mils of your sodium hydroxide there. So a lot of this stuff is, if you can reason through it, you don't have to worry about most things. You don't have to actually calculate anything. Just use your reasoning. So test taking skills right here. So that would be something to look at. Remember titrations. Oh, no, you just want to talk about buffers? Remember titrations with buffers have a very long pH range that will be about 1 pH unit between your pKa, right? pKa plus or minus 1. I have to take a picture of the creature because he's looking very cute right now. Okay. You want to do titrations. Okay. So, titration review. So, typically, let's do strong base titration. So let's look at the two options we have. If we have a strong acid plus a strong base, we're going to see that we have something plain sigmoidal like that, where this will be our equivalence point at around pH 7. And we start very low and we end very high. Strong acid, strong base titrations are boring. Who cares? Next. There's that kind of sharp increase, though. There's plain old sigmoidals, but nobody cares about those very much. If we look at a weak acid and a strong base, though, those are going to be a little bit more exciting. Those typically are flatter. They don't have this thing as much. Important points to note are the half equivalence point and your equivalence point. Half equivalence point, the pH equals the pKa at half equivalence. So don't forget that. Your equivalence point will be above 7 because you're going to end up having your weak base left over. The conjugate of your weak acid is going to be present in solution, which causes it to be basic. So your pH will be above 7 at your equivalence point. And we also start fairly high, so we're not going to start down at the 1s or 0s for our pH to start. We're going to start maybe 3, 4, 5 as our pH there. So start kind of just medium low there. If we flip things around and use acid now, boring, no one cares. Weak base though, notice we still have pH 7 at equivalence point, or very close to 7. However, with a weak base strong acid titration, it's going to be kind of the inverse of our first graph here. So we're going to kind of go down, have a quick slump, and then there we have it. That's really awful. Okay, let's try that again. Where we're going to just kind of deal with this. So here your pH will equal your pKb. Your equivalence point will be below 7, because just like before, now we have a weak acid in solution. That's going to end up having our pH be somewhere below 7. We're going to start medium high. For the other one, we start very high. Zooming through this, but that's okay. Important points to note though is that for weak base strong acid, at the equivalence point you're below 7. At the half equivalence you're equal to pKb. Actually no, it's gonna still be pKa, because pKb will give you hydroxide. So it's still gonna be the case there. So remember your pKa will be remember they you compare them with Kw, right? So 14. So 14 over your pKb will give you pKa. So at half equivalence, you're still looking at the same thing. You're looking at the pKa of your weak acid. It'll give you the right thing. Or you can say POH will equal pKb, but why would anybody ever say that? Don't even worry about it. Your equivalence point for a weak base strong acid titration is going to be below 7. Because you end up having weak acid around, that's going to lower your pH a little bit. For the opposite, weak acid, at half equivalence, pH pKa again. But at equivalence, we're above 7 because now we have a base chilling out there. So remember, the conjugates are still going to be weak bases of weak acids. So we're going to end up with slightly basic pH. Whereas with the other one, we end up with below. So 2-second crash course in titrations. Nobody cares about strong base, strong acid because they're just boring. They're just plain sigmoidal, like bloop. You end up very high pH, drastic change, now you're very low pH. With the weak stuff, you have more gradual changes happening. Don't forget, for your you might need ice tables. Remember, if you start with 0 of whatever, you'll end up with x squared over HA, whatever that happens to be. Again, we're assuming we can, with our assumption there. Or if we can't, we'll end up with this using our ice table. So don't forget, for weak acids and stuff, you will need to do an ice table. Or if you want to cheat, you can just go like this. But remember, if you already have A- or H+ in there due to common ion effect, you will end up reducing the amount your weak acid can dissociate. So that may also play a part there. So just remember common ion effect. Will lower the dissociation. So you'll be able to dissociate less if you already have H+ or A- in your solution already. But this will be for assuming you have 0 to start, so save yourself time. If you really want to do the ice table, go ahead. You may want to, if you have scratch paper, like have an ice table ready to go, have a couple maybe. Just save yourself some time, so just have stuff kind of set out. Prepare yourself that way if you like. So if you do want to end up doing a table, it's already constructed for you, just plug in the numbers and then go. So if that helps. What else can we have you guys prepare ahead of time? I don't know. It's up to you, I guess. You do have your formula sheet. Make sure you use it. It has all the formulas you need. You're not going to need formulas that aren't on there, so keep that in mind. You cannot always assume that. Don't use the quadratic formula. Use Wolfram Alpha. Save yourself some time. You can assume it if it's going to be less than 5%. So you just have to try it. If you get your X to be less than 5% of what your HA originally was, then it's fine. Then you don't need to use quadratics. However, if that's not the case, it may be wiser to just pop out Wolfram and do it there. Let me just check, though, if you're going to need that. Let's see. What questions did I include on this? That's not one of them. Not one of them. No. That one would be... So there is one, but its K value is really low, so it's very doubtful that you're going to have that problem. So I think your assumption will work there. So I only see... But here, I even gave you one on your practice. It is multiple choice, that's true. So one of the ones that I did give you was formic acid. God, it kills me to write it this way, but whatever. We'll do it that way. No, I can't. I have to write it this way. I'm sorry. Same thing. Its Ka is 1.8 times 10 to the minus 4. So if we have 0.0115 molar... Yeah. So let's go ahead and... Yeah, honestly, with Kevin's thing... it's going to be close enough. So x squared over 0.0115 equals 1.8 times 10 to the negative 4. Let's just go ahead and try the square root way. If we do it, so 1.8 times 10 to the negative 4 times 0.0115, square root this crap. We get x equals 0.00143. That looks to be like 10%, but whatever. Let's just see what we get. Let's try negative log of that thing. We get pH equals 2.84. And lo and behold, that's the answer. So, shortcut. Definitely. I would not worry about quadratics. So, with this, there's actually only even one number remotely close to this. And that is exactly what we got, which was 2.84 as part of the answer choices there. So, yeah, you can probably just go ahead and get away with it. So, yeah, that's the benefit of multiple choice, right? Is that you can kind of cheat that way. Alrighty. Anything else you'd like to go over since we are out of time here? If not, I do wish you the best of luck. If you've already taken your practice exam, I would suggest taking it again if you have time, maybe over the weekend. once more just closer, so you're getting used to the pacing of it and getting used to the type of questions, and see if this time you can try applying some of these, strategies where you can eliminate some answer choices right off the bat. So if you do have to guess, you at least are raising your chances. Yes, of course, we know sig figs are your doom. So thankfully, most of these they'll already have the sig figs done for you, so you don't have to worry about that. However, I think in the Gen Chem 1 version, they do have sig figs to worry about. So at least for a couple of problems on sig figs. Alrighty. Well, that's it then. So, awesome. We're done with 113. Well, I'm done with 113. No, I'm not. I have to grade stuff. Yes, right. See you in OChem. So, we'll have fun there. So, nope. Still, fall is still online. So, fun. Lucky us. So, hopefully, maybe in the spring we'll be online. I don't know how that's going to work because, because OChem 2 is a sequential, it's a course after OChem 1, it would be paying, so we have at least one student who's not in the area taking the class, so it would be impossible for them to continue the course. So maybe what they'll do is they'll have an online one and an in-person one in the spring. I don't know. And I think probably, well, I don't know for sure yet, the UCs and CSUs are all requiring their students to get vaccinated before they return to campus. So that would be something to get out of the way as well beforehand. So probably a good idea to get that done too while you have the opportunity. Well, we have lots of vaccine here, so. But we'll see how that's going to work. So at least fall, though, we're online still. So, alrighty. Well, here, let me upload this before I forget. We've done it. Awesome. On the register. Yeah, I know. At least with Ridgecrest, like I'd probably imagine they're not giving us tons of vaccine, but when I did it here, it was very, very fast. Like it took, like 3 minutes to actually get it, and then wait for 15 minutes. So of course I was dead the next day, but that's okay. I was okay the day after, so it's worth it. Alrighty, well, enough about that. Good luck. You can still type questions out. I'm happy to answer them in Discord. Just be aware that when you're actually taking the exam, if there's a question that you have, I would say don't waste time. If you have a second, shoot me a message on Discord. Hopefully I'll get it in time that I can respond. But, there's every chance that I might not be able to, so if there's a question, just kind of do your best with whatever information you have and move forward, just for time purposes. So you don't have the time to wait for me to respond. It doesn't hurt to throw the question out if you have it. If you're a fast typist, and you have Discord ready to go, but it may not be possible. So just keep that in mind. So hopefully the questions are self-explanatory. These are kind of vetted questions that have gone through cycles of students testing them, so there should not be any problems. So yeah, again, don't be ashamed if you have a really terrible score, because there's definitely going to be adjustment there. So all right, I'm done talking, so we'll be good. Alrighty, good luck everybody. See you in the fall.